Hello everyone, and welcome to the latest edition of IEEE VTS Young Professional Webinars. My name is Shadliya Ben Naila. I am Secretary of the IEEE VTS IP Young Professional Committee and the liaison of East Asia. Today we are delighted to have you with us for what promises to be an engaging and insightful session. It's my pleasure to introduce our speaker today, Dr. Lei Zhao. Dr. Lei Zhao received his PhD in Electrical and Computer Engineering from the University of Victoria, Canada in 2023, where he is currently a postdoctoral fellow and sessional lecturer. His research focuses mainly on federated learning and optimization with application in fine. And today, Dr. Zhao will introduce advanced ubiquitous intelligence through collaborative learning and intelligent data trading. We are incredibly fortunate to have Dr. Zhao with us today, and I am sure you will find his expertise enlightening and inspiring. Without further ado, please join me in welcoming Dr. Lei Zhao, and the floor is yours.
Okay, thank you very much, Professor Nila. It's my pleasure, it's my honor to be here to give you this presentation to introduce our innovations in the collaborative learning and the data trading. Okay, I will introduce all our techniques to target the issue that in the ubiquitous intelligence. As all know, in this society, we are focused on the vehicular technology, and in vehicular technology or in the future transportation systems, we would like to everything to be connected together, as it's a long-time vision. But now it's not only connected, communicate with each other. That is the communication technique we are developing now. But there is another part, is the intelligence. We want every part in this transportation system to become more intelligent compared with previously. Why more intelligent? With intelligent infrastructures or the vehicles or the devices on people along the roads, everything will become to much safer and smoother, and the confusion of the energy will be reduced a lot. It can save life, it can save your time, and it can also save our environments. Yeah, that is our big vision on all these techniques. Firstly, I will introduce several other applications. You can see they all need the intelligence everywhere, that we call it ubiquitous intelligence. And the intelligence everywhere, actually it means a lot of the devices, the IoT devices, the sensors, or the vehicles, larger as the vehicles, they all need to increase their intelligence. And their intelligence means in using the AI model to do their jobs, their tasks, in a more smarter way, such as in the manufacturing. Every device in the production line, any parts of it will be have the awareness of the demands, of the requirements, and this will make the scheduling much more smarter, and also identify some issues that could cause big issues in later, and they can predict that issues and solve it before it happens. So make all the production lines much more smoother and with no time to stop the production line to fix some part. Yeah, the maintenance is can be much more. The maintenance could be much more smarter to detect all the issues in the smart manufacturing. Also, we know it's another technique is the digital twin, right? We want to use a digital twin to be the bridge to combining in the physical world and the virtual world, the digital worlds. And this technique is very useful to do some to visualize some complex systems or to do some simulations. And when you design some very complex objects, or you have some planning for your scheduling, you can use this virtual visualization or virtual reality, and also based on the digital twins to make more smarter decisions by combining all the data in the virtualized digital worlds. But all these applications, actually, as I have mentioned, we are moving in the direction that we would like to make them much more smarter, right? Intelligent. The intelligence comes from where? Comes from the model, the large model that we are based on currently. And if the large, what is the large model is learning? They are learning from the data, right? As Ilya have said this idea several days ago in Vancouver in the NIPS 2024, he just said that we have achieved the peak data. It means there is no more additional available data in the internet. And in this case, if we continue to increase the capacity of the model in the physical way, actually they will not learn, do not learn anymore to improve their capacity in the intelligent task, dealing with the intelligent tasks. And that is, he has mentioned that there is a direction that to increase the reasoning capacity of the agent. Each agent could only rely on very small sites of the data samples, and they rely more on their reasoning capacity. That means, but in this way, it's very promising, and it's the trends. But in this way, it's there is a challenge. It means you have more reasoning that you just based on very limited data, very limited data from the reality, and then the rest part you are just the reasoning, and it means there is a lot more unpredictable things will come out. The decision cannot be predictable, and also you cannot guarantee it always be correct, right? That is the issue. So in my research in this topic, actually I have introduced that two parts. The first part is a collaborative learning, as we all very familiar with it. Actually, we are familiar. It's a very hot topic in current research. It's the federated learning. In the federated learning, it's actually it means the common data. That means the data on the internet is achieve its peak, but there is a lot of hidden data, such as in the applications I have mentioned. They are personalized data. They are private data. They cannot be shared for each one, and you collect them all together to training them centralized. So that comes from this federated learning. In federated learning, there is a central model. That model is will perform the same task as the centralized training model, but the training procedure is not in the data center set, but it's in each individual agents. Each individual agents will apply its local data and to training its local model, and the data will feed. Actually, from this way, you can see there. From its, I just gave you the very big overview of this structure of the collaborative learning. We will have our orientation is to optimize optimal objective function. That is our original intention. We do the training, want to achieve that. But in federated learning, when you perform the training procedure locally, you have a lot of thousands of agents to training their local model based on their local data sets. You will have a lot of different targets, as I have shown in the bottom. The FI, it's for each agent, for each local client, they training their local model because they training their local model based on their own observations, their data they have generated or they have observed, or they just have that kind of data. And that kind of data will be very, very different from each other. And also we know the objective function, it can shape the landscape of the objective. The data can shape the landscape of the objective function. You have different data sets. Your objective will be different. When you do the training procedure, actually you are tuning your model parameters in the different directions. That comes to the challenge that you cannot combining with the challenges when you're trying to aggregate all their individual insights together. It will be very hard to convert. And also it's inefficient in the training procedure because you will always make compromise when you're trying to combining the individual models, right? Because each one is updating the different directions. You're combining them together, such as in the very beginning, the Fed AVG. You will actually that step is compromised in each for each agent's efforts, and it will drag you back a little bit in the central updating the central aggregation. And that is our research target. We have developed different techniques to solve this problem. Firstly, we just start from the feature engineering. As we know, all these local data sets, they have different updating targets because their data features are so different from each other. And then it will give us a sense if we can reduce the heterogeneity among all the feature vectors from different local data sets, maybe it will increase the efficiency of the entire federated learning procedure. That is our first target in the work by applying the transformation domain features. And the second work is the major innovation in our your research. We know the training procedure is it's in the local. Yeah, the model is tuned in the model. In the global, the traditional way, in the global, for the federated learning, they just collect all the insights from individuals and just weightedly sum them together, and then redistribute them to each clients, to each agent, to retraining them locally. Based on this idea, actually, we observe that they can collect the individual local model and also the individual training dynamics to the center. It means the model parameters and the gradient information. We have both. We can apply optimization methods in the center to make further acceleration in the tuning procedure. And this tuning procedure will be based on all the overview of all the participated clients' vision about how to tune their model, and it will reduce the jitters in the updating, and also greatly accelerate the convergence speed. And the second part is the data trading markets. As we know, the peak of the data, it's from the common data. It's achieved its peak. There is no more generated by humans that could be shared with each other on the internet. That conclusion is based on the idea that we only have one internet. But except the data in the internet, we have a lot of data islands. That is the huge amount of data that we cannot see it in public. It comes from the data trading marketplace. Making this data trading marketplace can make all these unseen data be available if they have ownerships, and they can make tradings with them, get profits from the data they have owned. It will be more incentive for the individuals to share the data. That is our second part. Okay. Now let's go into the very detail about our first topic in the feature transformation domain to training to do the local training, and then it will have advantage when we globally aggregate all the local models together. The performance will be much better than the previous one, because this innovation comes from the intuitive idea that when we check each feature, such as in this example, the IoT devices, the camera each camera can be regarded as one agent, and it observes one corner of the street, right? Different cameras will have different angles, different streets, different scenarios. Their collected samples are different. And maybe that camera belongs to that company, that camera belongs to another company. They do not want to share their information. And when they do the local training, just based on their original sample, their objective function will look very different from each other. Their target, their efforts, when they make updatings locally, their efforts will lead them into different directions. They will converge into different optimizers minimizers. In that case, it's to solve this problem, we just transform the original feature into the frequency domain. By check the features into the frequency domain, it can greatly reduce this heterogeneity. And more, we can as in our, you can check our paper in has been published 2 years ago, and in this paper, it's we have proposed different transformation techniques, such as from the discrete cosine transformation or discrete wavelet transformation with 1D and 2D images. And in this results, it can show the performance compared with the very basic baseline federated average algorithm. Our performance can increase hugely, and this performance is not only based on the frequency features, but in this results is showing you is there is a C DCT. It means C is combination. We combining the frequency features with its original time domain features together, and then do the training. The performance can be greatly enhanced. In this research, actually, there is one open issue, and maybe you are very familiar, you are very interested, and can lead into your future researches. It means the frequency selection problem. In here, without the frequency domain, in the frequency domain, there will be infinite frequencies we can select. And in here, we just use very simple the discrete cosine transformation. It's discrete. We have very limited. Just select 0.001 portion of the frequencies. We focus on the low frequency domain, and just select that part of the frequency and to be the enhanced feature. But there is a very tricky, very challenge problem. It means which frequency bands should you select to represent your features and to make the training procedure much more efficient and better. The second topic is about the central acceleration. In this the central acceleration, as I have explained previously, we collect all the local models, and based on their local training dynamic information, their local gradients, all goes to the global to the cloud data center or to the central server. And inside of the central server, we have applied different optimizers, the conjugated gradient descent optimizer to accelerate the updating, or the adaptive central acceleration, or use the natural central acceleration, and with a deterministic client selection. The advantage of this central acceleration is it enhances the entire training procedure greatly. Why it can increase as you have okay, that is the formulation. Why it can enhance the training procedure a lot greatly is based on the idea that you see here is anchor gradient. This anchor gradient is the current collection of all the vision from all the from the agents from all the clients, individual client. And each client just calculate its local gradient based on the current global model. And they will transmit that gradient information back to the center. And in the center, it will have the vision that, yeah, each client, they have their vision about their individual vision about how to make the adjustment. The gradient will tell you where to tune in your model parameters, right? Because the target of the training procedure actually is the optimization procedure, trying to figure out the stationary points, minimize their gradients. In this way, it's the global central server will have the entire view of each individual's vision, and they can use different techniques in optimization to based on these building blocks of the individual gradient to derive the global updating direction as DR-1 here. The global updating direction. Make one step global updating further. It can greatly increase the performance of the federated learning. Also, in the local model, in the local training procedure, we also have introduced we also have applied this variance reduction technique, because as I have said, each individual, when they do the local training, they are making movements locally. They need some guidance to tell them to not move so far away. Who can do that job? Only the global, right? The global model, the global vision can get them. Do not go too far away, because the global vision is a common vision from everyone. We are collaborate together actually we want to work together to do the training procedure. So we need to agree with each other where should be the good research direction, where should be the good updating directions, and how far we can move away, cannot move away so far away. And that is the idea in our local training. And you can see the results from one example from our published paper in the TCT this year. And this is based on the conjugate gradient descent central acceleration and with the inexact line search we have developed. In this way, you can see that it converged very fastly in based on their training training procedure in the first figure, with only 5% of clients participated from out of I remember it's 400 clients in total. And the second part is the testing accuracy. You can see our method can converge fastly and converge to a very higher accuracy, testing accuracy, and that is the efficiency of the central acceleration. Yeah, that is a federated learning. It can enhance the actually it can we are designing new architectures of the federated learning and or the feature engineering in the local data sets to enhance the performance of the federated learning. And well, I'm saying this direction is not new, but you can see this direction as some solution to the data peak challenge for the future AI development. And another direction to target that data peak challenge, as I have mentioned, is data trading. This one is in my vision about the data ecosystems. It's we need if we want what is the ideal world. Ideal world for the AI training is we can get every data we want. We can use apply them to training our model, right? It's but that is not in the reality. We know huge amount of data is locally it's local data, it's private data. We cannot share them. And you want them to move fluently, right? You move fluently. Yeah. When you train, when you design one application, you would like that kind of data, and you would like it to fill your model in the training procedure. How could you get it smoothly? You cannot get it just ask, right? You cannot get it just by asking. You need that is why we developed this data trading platform. It can move all the data, local personal data, actually personalized data, to be useful to the application demands, the AI intelligent applications in the ubiquitous intelligence, and to make this training procedure actually, I mean, when you fetching the data with this procedure will be very smooth, much smoother if we want to pay some price for it. Okay, then in this case, it means we need to develop this marketplace for the data trading purpose. And as we know, the in our next work, we have developed such trading marketplace and focus on maximize its revenue and control the risk locally. And this is as we know, it's all these data trading. Actually, it's it can also generate a lot of different products. Actually, there is an ecosystem. Just you can imagine the fossil fuel, right? The fossil fuel, we drill it from the underground, and there is a lot of side products from the original fossil fuel. The data is the same. The original data is original data, but based on the original data, there is a lot of products, data products can be generated. Or currently there are many big companies. They are not only relying on real data because real data is very limited. They also build up models to make the generated data. They are synthetic data, which will be more similar to the reality, but in a huge amount. That data, they will not share it. And they will just use it to training their own model, such as the self-driving cars. Their model is their property, right? Their core property from their company. And in this way, it's if you there is another company would like to get utilize that kind of data, he or she need to pay some price for it. Okay, that is what I mean. It's based on this marketplace. There will be a line of different business will be developed, and there will be a lot of new innovations, and based on this idea. But there is a challenges in the data trading. Firstly, when we trade some such as the physical objectives, we buy a car, we buy something, right? We can see it. We buy a clothes, we can feel it, and the buy or not to buy, sell or not sell, that decision is made by human. But when it comes to the data, some kind of data, yeah, it can be supervised by human, yeah, that kind of, such as some documents or some data static data in there. But in my vision, it's there are a lot of data actually is generated by a bunch of different sensors or different devices. The machine, such as the machine, will generate data when it's doing its work, such as in smart manufacturing, in the transportation system. Every vehicle will generating data at every minute, right? A huge amount of data is generated. And this trading decision cannot be made by human, because human is not available to interaction with that trading procedure. It's in a very high frequency way. And also the data is very challenging for the humans to decide what should be the price. How could I make the exchanges with other agents, right? That is also the idea from the Eli. He said that in the future, all the agents will automatically dealing with different softwares and make decisions to perform different tasks. In that way, in our vision, we have introduced this autonomous economic agents. That agents can replace the human to conduct this trading procedure. And based on this agent, it can receive the it requires real data, and there will be the critical part for the agents to do is to do the trading decision. And for the trading, the data is automatically collected. Yeah, we know that because they are automatically generated, a lot of them, and also they need to be automatically collected. And the data production is not just produced by human, right? It should also be produced by some machine. And that means the entire marketplace, there is no human interaction. They are all dealing with each other, trading the data and build up, generating the data products by themselves. That is a target for this AEA. We call it autonomous economic agents. Can represent each actually each company or each individual person can manage your wallet, not for your entire fortune, but just the part that you would like to invest into the data trading market. Yeah, the totally management of your wallet is based on this agent. So that is I just draw a very simple figure in here to show how this procedure is going. And just for you see for these agents, they need to there is another level of task that need to be collaborate. It's no longer collaborate on the original machine model that targeting your specific applications, right? Such as self-driving cars or the machines in the factory. They have specific tasks, and they need specific models to do that task. And they training it collaboratively, federated training. In the first part in my topic is that target. And now in the second part, my topic is about a different target. Yeah, the data would be trading in this marketplace. It means the data actually is flowing everywhere. It's just like the blood to power the future artificial intelligence. And in this way, it's if to make this flowing of the data product smoother and efficiently, it means we need to make this automatically trading platform much more efficient and effective. So that means the AEA, that agent, the economic agent, should do a very complex task. But each individual, as in our previous federated learning, the same as each individual clients have its individual local data set. Now each individual client have its individual AEAs could be, and this AEA they want to sell or buy the data products from this market, and all these decisions based on this economic agents, and the model actually inside this autonomic inside this AEA also needed to be trained in the federated way, in the collaborative way, because you do not want others to check your usage, right? What kind of data you are using, you are consuming, what kind of data you are selling, you are selling and generating in your local. That is another kind of data. The financial data, individual financial data, is about the data product, is also need to be protected. That is our last target by applying the federated learning again to training the trading model within this autonomous economic agents. And for here we have encounter the new challenges in this new marketplace. And we firstly, actually, it's the target. You need to I mean the objective function to tune your model. We need to design new objective functions, new targets in this financial area. And this our initialized work is this work is a very simple one. And in this work, actually, we develop this marketplace by designing its objective function. That is a major part of it. And the second major part of it is trying to still utilize the feature engineering techniques to combine the histogram oriented gradients with discrete wavelet transformation to pre-processing all the raw pricing data of all different data products, and to improve the training procedure. Also, in this from the technical way, not along the innovation in the market development, but in the technician way, in the federated learning, there is another innovation in this work. It's about when we trying to combining aggregate the local models together, we no longer aggregate the local models just based on their time domain. We aggregate them in the frequency domain and then transform the frequencies after the aggregation back into the time domain, then continue to do the next round of the federated training. Yeah, that is one example from the results. And as we can see, we use the target of the Sharpe ratio as a target. Sharpe ratio is terminology from the financial area. It just means the ratio from the return, and you can understand as the return with the risk. We minimize the risk, increase the return, and then that it becomes to our target. The larger this one will be, the better the performances. It means you are make more profits with very limited risk. Okay, that's all. Thank you. Any questions? Do I still have time? Yeah.
Thank you very much, Dr. Leizao, for this very interesting, actually, and insightful presentation. Yeah, I have a few questions for you, so, and I hope you'll be answering my questions. First of all, can you go please to the slide number 9, where you are talking about frequency features, I think.
Yeah.
Here. Could you please explain further how you proceed actually? here where you were talking actually about the usefulness of the frequency features. Could you explain a little bit more, please?
Yeah, it's this is just a very simple example. It's showing the frequency features by just doing the discrete cosine transformation. This idea comes from that there are real in the time domain features as shown in above. These two figures may be different and very different. Heterogeneous comes from that part, and then we transform them into another domain, another space. Actually, re-represent each other, and their heterogeneous of them will be. I hope they will be reduced a lot. And in this one, when we do this discrete in this method, when we do this transform, it's because it's we just focus on these parts, the first 0.01 portion of the frequency features. It means they are in the low frequency domain. Here is the low frequency part, and we ignore the higher frequencies because the details will be the very details. It will be inside the high frequencies. We actually there is still some very critical information inside. Yeah, that will be the shortage of this current work. As I have mentioned, you can move forward to decide which band, which area of the band of these frequencies will you utilize to design this new representation.
Yeah, indeed. Yeah, thank you for your explanation. Indeed, I was actually my second question or my next question was about. You can hear me?
I can hear you.
Okay, yeah, sorry for any inconvenience. Yeah, so earlier, yeah, I was saying, yeah, actually you just how to say, my next question was actually about the choice when you were mentioning the challenge in, I think it was in slide number 11, where you are talking about the challenge to select the frequency band. And yeah, I would appreciate it if you could expand more actually about this challenge, why it's a challenge actually to select the frequency band.
Yeah, thank you for the question. It's challenges means such as when you do the in the time domain features, we do feature engineering. Actually, we are such as for when we try to reduce the feature reduction, we regenerate new latent features. And in the frequency domain, I mean, it's just in the first step. When we transform them into the frequency domain, there are a lot of frequency. Each frequency just be the building block for this new representation. And I mean, the challenge to select is you do not know. Actually, we do not know which part of the frequency we should involve to represent these new features in the frequency domain. We do if we apply all of them. Actually, it is also the dimensionality. It's a curse of dimensionality. It's very huge amount. We need to select such as the feature reduction. And the second motivation that why we need to select the features, because discrete Fourier transform is just a very simple transformation way. In real, if we do the real Fourier transform, it's the frequency will be the frequencies actually it will be infinite frequencies to represent the original feature. It is very important to target which frequency is very important, and based on this idea, we have the new actually development. That is feature analysis. Actually, feature analysis in the frequency domain. We have another work is talking about model parameter analysis in the frequency domain. We do not say in the frequency domain, but we say we transform the model parameter because the current model parameter is very huge, especially for deep learning models. Many parameters in there, and the analysis is very hard to make it robust and to make it explainable. It's very hard to explain how the training dynamics works. And now one way is we just propose that we can transform them into the Hilbert space, which is similar. The idea when we understand it, similar as a Fourier transform. There will be infinite dimensions to represent your original. If we stack all the parameters into one vector, there will be infinite dimensions to represent your model, represent the model parameters. And the training of the original deep learning models training procedure now can be explained with inner products, because the Hilbert space is inner product space. And then the model actually becomes to a linear model in that space. But the challenge, similar as here, you have asked, why should we do the frequency selection? Because there's infinite frequencies. The dimension is infinity. And when we should focus on which part is more important, just similar as the principal components we need to target in the training data sets. Yeah, it's similar targets.
Yeah, indeed. Thank you. Thank you very much, actually, for the fruitful explanation. I would like to move on to the next question of mine. Could you please go to the next, not the next one, the one after, actually, number 13, slide number 13, where you were talking about global, could you here explain further? You were talking about the global model and the local model, and you are comparing both of them. Could you please explain further about the content of this slide? Yeah, those both models, please.
Okay. Thank you. Thank you for the question. Firstly, it's a global model is in the left part is global model acceleration. We use this W R-1 refers to the current global model. And we want to update it in one-step updating acceleration inside that central server without data, but it needs the gradients. We know in the entire training procedure, the dynamic of the training procedure comes from two parts: the model parameter and the gradient. They are dancing with each other, and based on the data, given your data, given your target, and we can generate the gradient from the model parameter. The local side do not need to transform the data to the center, but it needs to transform the gradient to the center. I regard the gradient, local gradients, as a vision from the local data sets, the local intelligence. They are telling you that, I would like to move to that way and to tuning the model. It will perform good, minimize my objective. Another one will tell you, I need to move that way to minimize my objective. They have different objectives. So their moments is different, and their moments is reflected by their local gradients. In here, I use one unique global model and given them, and they based on that model and their local data sets to generate another part in the dynamics of their gradients, and they aggregate them together in the center. And based on this gradient, we can apply very fancy and complex optimization techniques to improve the model, updating the global model one step. And in this updating, it's efficient. The most important reason is that they're updating the direction, the global model updating direction. Actually, it comes from it's already one aggregation from each other, from the individual's insights. And in the local model drives in here, we also apply this global model to be some anchor. The global gradient, the anchor, to be some anchor to get each one to do the local updatings, to minimize the variance in the local updating.
I see. Okay, thank you very much. Can we go please to the next slide? Just the one after, number 14. You were presenting some interesting, actually, experimental results here. So let me confirm. The proposed method is the one represented by the pink curve. Am I wrong?
Yeah, the pink one, the last two actually. It's the pink one is the black one.
Okay, so this is basically the method you propose in your work published in the IEEE transaction, right, on the kinetic.
Yeah.
Can you summarize, like, very briefly, what is the main feature of your proposed method compared to the other existing actually methods?
Yeah, this method actually is from all these this above baselines. They are just they are different methods in to improve the federated learning efficiency. But they our method can be very powerful. Actually, it can be integrated with each one. Each one of them do not do too much in the central central server, and our method is in the central server we can based on the collected gradients and innovations in the updating in the center to improve this performance. Actually, this method is also can be extended a lot based on its conjugate gradient descent. We know the conjugate directions is very performs very effectively with quadratic problems, right? The quadratic. But we know the objective function in the deep learning training, the models, they are not, most of the machine learning models, they are not quadratic functions. And how could we make this much more effective? Actually, there is one idea to do it. We, in my entire research, actually, if you follow my research, the entire direction is moving in the direction that we want to make the model much more simpler. And then in this way, we are seeing simpler model will become more robust to the new noise we have never seen. And also it will be much more explainable compared with its original model. So this idea is not just the end-to-end, yeah, we directly apply that simpler model, not in that way. In the training, we apply this idea inside the training procedure. It means in the previously, you make one updating from WT minus 1 to WT in one iteration, right? It's this iteration in our case in the central server, and this iteration is also based can be decomposed into several steps, and these several steps will make great improvements based on the conjugate direction generation. And this, if we just you are standing at this point, such as in our global model WR-1, you are standing at that point in the global. Based on that point, we can have the estimation of the global objective function. We can apply the Taylor expansion, second order Taylor expansion to get the quadratic approximation, and then we can get the statistical Hessian in there. If your model is so large, you cannot do the second order derivative. Actually, we can approximate the Hessian matrix based on the current readings. Yeah. In that way, I mean the nested updatings in 2 points to make this much more efficient. Based on the conjugate directions generated.
So basically, if I get your point, usually we start from a simple, simple representation to the more complex model. But earlier from your explanation, if I get your point, it's the opposite. So basically, an efficient method, it's the one, like you start with a more complex representation, go into a more simple, understandable, and self-explanatory method. If I got your point, is my understanding correct? Basically, this is the direction you are talking about, explaining like this is the next step actually. After is my understanding correct, right? I got your point, right?
Let me make it
quite understandable. Quite interesting actually. Usually we start with it's a simple for example in communication, it's a simple representation, and then you're gonna add more feeding factors, for example, and it's gonna be more complicated, more complex. But now what you were explaining,
reduce the complexity.
Indeed, more understandable. It can be explainable, as you said, the word used earlier, and basically more simpler. It's quite interesting, actually. So, sure.
You can go ahead.
Go ahead. Okay. No, I was because I still have a couple of questions, so I was thinking to move on to that.
I can answer this question. It's not. It's not.
Sure.
It's one part. It's make the model simplified. And that is only in the I'm talking about in the training dynamic, in the training procedures. We are making tunings on the models because it's we need a lot of hardwares, GPUs, and a lot of electricity to train the model. It's very resource consuming, and to make this one training procedure to greatly accelerate it and make the training procedure more friendly for the energy. It's I just see.
I got your point. Yeah.
During the training procedure. Yeah. During the updating.
And indeed, so like I think I got your point. So basically, this is about the training part. For the training part, it's like improving means you have to simplify the training process to consume less and go for a green, actually, like more energy efficient, if I may say, like training process. Yeah, I thank you very much for the clarification. Let me now go to the second part, actually, because basically in your presentation today, in our webinar today, you talked about two main topics. If I could follow actually your explanation, you were talking also about data trading, like started from the page 16. I would appreciate it if you can go to the slide 18, where you were introducing the challenges. Here you were talking about the challenges of the data trading. So can you clarify a little bit actually more about the main challenges of the data trading?
Thank you for the question. It's the first challenge is the common one, from same as in the federated learning. It's the traditional one, and I think in the data training market, the unique challenge comes from the data's ownership and the data quality. It's the new challenge comes from, firstly, when we want to trade something, actually it's we have the rights to trade it and copyrights to trade it. We have the ownership on it. Yeah, that can be defined. If that is your data, that is the data you have bought, and you can trade it or not trade it. That is one challenge. Another challenge is that is also a very common challenge in the entire financial areas research is the pricing problem. We in finance they will do the asset pricing problem. All the models, very sophisticated pricing models, trying to determine what should be the true price for that asset, for that product, and for that stock. And this is even becomes to even more challenge for data. Why? Because even the same data product, the utility of that same data product to different companies or to different applications will be totally different. I mean, its value will be changed a lot. Someone is using it. Maybe it's just I can use it. I can use another. I can even not use it. That means its value for that person or that a machine is very limited. For another one, is that kind of data is a very valuable data, very valuable insights to tuning their model, to increase their model's capacity, and they would like to pay more for that data product. It means that the data product's quality to different applications will vary a lot. It will be much challenge to determine the actual price we should pay for that product.
I see. Thank you. And I still have a couple of minutes actually, and I will go to the my last question here. Can you go please? I think to page the slide 23, where you were introducing a rough, maybe not that one, where you were introducing kind of model, and you said that this is. You were explaining about the difference with the existing model. Maybe page 20 then. You said this is a rough, this one. Yeah. What is the main actually difference with the existing or the previous model?
It's I mean the model is it's task. In the previous the model is directly dealing with the task the machines, the individual machines in each clients they are doing, such as each real applications, directly training the model to power that application. In here, this model is not to power all the different the applications, but it's powering the training model. The training model is still there is a lot of different applications, and they need the data. And not in here. This model is not about the applications model. It's about the data trading model. The model that could make the decision whether to sell that data product or buy that data product, to then just directly based on the data it owned, to training its own model for their own application. Yeah, that is the difference from the previous part.
I see. Thank you very much for actually answering my questions. And with this question, actually, we almost come to the end of our webinar. Thank you again, Dr. Leza, for your insightful presentation today. We learned a lot. I appreciate your availability today to be among us for this webinar. And with this, we come to the end of our webinar. Thank you very much.
Thank you very much, Professor. And yeah, have a nice coming holidays.
Yeah, I wish you the best for you and your family, of course. Yeah, I wish you a nice break and nice holidays. Thank you very much.
Thank you very much.
Thank you.